Okay, so wonderful good morning everyone. I welcome you back to my YouTube channel. Presenting before you this wonderful tutorial is Harmonic. So today we will be looking at simple harmonic motion, and of course to those of you that are new, make sure that you subscribe to this YouTube channel and also don't forget to share to others. So if you have a question, make sure that you inbox me on WhatsApp, just on this same WhatsApp line which appears to be on the screen. And of course, these are our objectives. We're going to define what simple harmonic motion is. We are going to look at the relationship between Hooke's law and simple harmonic motion, and we're also going to look at the formulas for simple harmonic motion, the three formulas, of course, that are very important that you are supposed to know. We are also going to look at the energies, the formulas that you are supposed to know for the energy, and simply how to derive them. Okay, then of course in my other tutorial I'm going to show you just how to answer practice questions, especially under simple harmonic motion. Let's get started. So by definition, what is simple harmonic motion? Simple harmonic motion is simply the motion in which the restoring force is directly proportional to the displacement of the body from its mean position. And by mean position, we're simply talking about its initial position. Okay, so the direction of this restoring force that we're simply talking about is simply is simply towards the mean position or the equilibrium position. Okay, so when you're talking about simple harmonic motion, you are simply considering objects that are capable of being stretched to some position, but at the same time being able to be restored back to their initial position. So for example, let's say let's say for example, of course, you have a spring of this kind. Okay, so let's say this is a body of mass. Okay, of some mass. You have a body here, of mass. Okay. You discover that if you push this force in this direction using, let's say, you apply 10 newtons on this spring, then of course you are going to expect something like this to happen. The spring is going to be compressed in this direction. Course, in this direction. But then you discover that if you release this spring, then of course the spring is going to move in this direction. It's going first of all to compress like this in this direction, okay, at some speed v equal to, we don't know, but then you discover that as this spring is being compressed in this direction, the spring would desire to go back again in this direction till it gets back to its initial resting position. So this is just what simple harmonic motion is. Okay, we are simply talking about objects that are capable of being compressed to some position, but at the same time they are capable of getting back to their initial position. So now let's talk about Hooke's law so that you'll be able to understand, because it is the basic foundation of everything. Now I want you to imagine something. Imagine that you have a spring of this kind. Okay, let's say you have a hand wire like that. Then here you attach a spring with an object of mass, let's say equal to 60 kg. Okay, now let's say this is just illustration 1. You discover that if at all you apply a force on this object of, let's say, 20 newtons, then of course we expect this thing to compress in this direction. Okay, this direction. But then you discover that the difference between the two is simply their length. So you discover that here maybe it can be 10 meters, but if you apply that force, then you discover that this thing is going to increase. Okay, so this thing will compress down there. It will increase, maybe to double to 20 meters. So what you're simply doing here is you're applying a force in this direction, and this force is simply what we are calling as the mg. It is measured in newtons. Okay, but at the same time you discover that the more you apply the force, the more this distance is simply increasing, and the less the force, you discover that the less the distance is going to increase. Therefore, to those of you that doing mathematics, I'm sure you know what is happening here. If you increase the force and you discover that the distance is also increasing, it simply means that the force is directly proportional to the displacement. So, having deduced that relationship, we can now say that the force was directly proportional to the displacement. But notice that the force is applied in the negative direction, which is down there, in this direction. Therefore, we can simply say that this displacement is going to be stretched in the negative direction. But remember that since this force is directly proportional to this guy, there is this relationship between the two. There is this relationship between the two, meaning we're supposed to apply a constant k here. So meaning our force is going to equal to negative kx. So this is the formula for Hooke's law. And Hooke's law simply states that the strain of a material is proportional to applied stress within the elastic limit of that material. The stress is simply the force, and the strain is simply some distance that is covered after applying that force. But then I want you to take note of something. Remember that the force is equal to ma. We know this formula. But then, having known that force is equal to negative Ka, while there is this force, I can simply replace with this expression so that I can have MA equal to negative KX. Then I can cancel with M and cancel with M. I'm going to remain with A equal to negative KX over M. But then I want you to take note of something. There is a formula that I want you to take note of, which is very important. Let me write it here. One thing that you must know is that there is what we call omega, which is also known as the angular frequency. Okay, angular frequency. Okay, so angular frequency is measured in radians per second. Okay, now this angular frequency or omega, let me just try to wrap this. Okay, so the angular frequency is measured in radians per second. Take note of that, it's very important. Now omega is equal to, let me show you something. Okay, now omega is equal to the root of K over M. Now this K is called the spring constant. The spring constant. M represents the mass in kg. So now if we square this and square this, you discover that omega squared will equal to K over M. Now in this formula, what there is K over M, I can replace with omega squared, then X. So this formula is what we'll be using to calculate the acceleration. Take note of that. Okay, so you can also take note of this formula. Sorry about that. You can also take note of this formula here. You can also take note of let me try to wrap this. You also take note of this formula that I'm going to write here, which is just omega is equal to root of K over M. I'm going to be using this formula quite a lot, so make sure that you take note of it. Alright, so this is what you're supposed to know about Hooke's law and simple harmonic motion. Now we can get to the derivation of the formulas. Okay, but before we talk about the derivation of the formulas, let me talk about the formulas for simple harmonic motion. Okay, let me go to my other page, blank page. Now, for simple harmonic motion formulas, you are supposed to know these very important formulas. The first formula that you have to know is displacement is equal to A cosine WT plus phase. Okay, make sure you know that formula. we can label this as formula 1. The second formula is for the acceleration. Acceleration is equal to, okay, so this negative a w squared cosine wt plus phase. So you can also take note of this formula. It's very important. The third formula that you have to take note of is for the velocity under simple harmonic motion. The velocity is given by the formula a w, where w is omega in radians per second. Now instead of putting the cosine, we'll put a sine angle, so it will be sine wt plus phase. Okay, label that as formula 3. Okay, now remember that, let me try to draw something here. If this is your spring, you have a mass here in kgs, sorry, the mass in kgs, you discover that this thing, if you compress this thing in this direction, applying a force, then automatically you are applying a certain energy, which we are simply calling as the kinetic energy. And remember, I said that this spring is capable of being compressed back because it so desires that it goes back to its initial resting position, okay, the position where it will rest. So at the point of rest, it's going to have some energy which we are calling as potential energy. But then remember that when this everything is now restored, the total energy is simply a combination of the kinetic energy plus the potential energy. Okay, so this is very simple. Now from here, one thing that you must be able to know is the total energy is equal to 1 over 2 K A to the power 2, where K is the spring constant and A okay. Okay, so okay, so we have the total energy equal to okay, sorry, we have the total energy equal to 1 over 2 Ka to the power Ka squared. So another formula that you have to know is that, let me just try to write it down here. The kinetic energy is equal to 1 over 2, sorry, 1 over 2 mv to the power 2. Doesn't change, it's just the same. Okay, so we can name this one as formula 4 and this one as formula 5. Okay, so we can say 6. Of course, the potential energy under this topic is equal to 1 over 2 k, where the k is the spring constant kx to the power 2. Okay, so you know that formula. Make sure you know these formulas. They are very important. Let's try to derive some formulas, of course. Now let me try to show you something very important that you also have to take note. Remember that if this is our spring, remember that if you pull it in this direction using some force, then of course we expect it to accelerate to some distance using some velocity. So now the acceleration, I think I showed you how to come up with the formula for the acceleration under simple harmonic motion. I said we know that the formula for Hooke's law is simply negative kx, and then we know that the force itself is just ma. So while there is this force, I can replace with ma so that I can have negative kx. Then if you cancel everything over m, you are going to come up with a equal to negative k over mx. Remember omega, say that omega is equal to the root of k over m, meaning if you cancel this, then you introduce a square here, meaning omega squared is equal to k over m, meaning while there is this guy here, I'm going to replace with omega squared x, and this is our formula for the acceleration. Okay, now let's come up with the formula for the total energy. We see how you can derive the formula for the total energy. Okay, let me just try wrap this. All right, now there are formulas that I want you to remember. Remember, I said that the velocity under simple harmonic motion is calculated using this formula, sine wt plus phase. Then for the displacement, remember it was a cosine wt plus phase. From these formulas we can come up with the total energy, because remember we said that the total energy is equal to total energy is equal to 1 over Ka squared. So it is this formula that we want to come up with. So now to come up with that formula, remember that total energy is equal to the potential energy plus the kinetic energy. Now we know that the potential energy is simply 1 over 2 kx to the power 2, plus for the kinetic energy we said that it's going to be 1 over 2 mv squared. Okay, mv squared. Let me just try wrap this. Now if we have these formulas, then it simply means that I can replace where there is this x with this displacement here. Okay, let me just do the replacement. So I'm going to have a cosine wt plus phase squared plus 1 over 2 m then of course I'm going to replace where there is this V with the formula that I've highlighted down there. So it's going to be A W sine WT plus phase squared. From here we're going to have 1 over 2 K. Of course, since we've squared everything in here, we're going to have A squared, then cosine squared WT plus phase. So you can't square this because this is just like an angle, plus 1 over 2 M. Then since we've squared everything, we're going to have A squared W squared sine squared WT plus phase. From here, remember that W to the power 2 is just the same as omega. This is omega squared. So remember, omega squared, we said that it's just equivalent to W equal to K over M. You can do the replacement there. We're going to have 1 over 2 Ka, then cosine squared WT plus phase plus 1 over 2 M A squared. Then here I'm going to put K over M sine squared WT plus phase. Then of course this mass and this are going to cancel, and we're going to remain with 1 over 2 Ka to the power 2, then cosine squared WT plus phase. Then of course we're going to add everything to okay. So all right, let me just get my pen. So of course, if that will cancel, we're going to remain with this K. So the K is going to remain. So we're going to have K A squared so of course going to have sine squared WT plus phase. Now notice that we have Ka to the power 2, Ka to the power 2. We have 1 over 2, so we can factorize everything. So when we factorize, we're going to have 1 over 2. So we're going to factor out Ka to the power 2. Then of course we're going to remain with cosine squared WT plus phase plus sine squared WT plus phase. Now remember that this is a trig identity. Let me just try to wrap this. Now remember that this is a trig identity. This is a trig identity and it is equivalent to 1. So this simply means that we're going to have 1 over 2 Ka 1. Therefore our total energy is going to equal to 1 over 2 Ka to the power 2. So this is just the formula for the total energy. Make sure that you remember this formula. So So make sure that you remember this formula for the total energy. It's very simple. Okay, so now let's get to show how we can find the velocity. Now for the velocity, remember we said that the total energy is equal to potential energy plus kinetic energy. So total energy, we say that it is equal to 1 over 2 k to the power 2 equal to, then of course this is going to be 1 over 2, because we know potential energy was equal to kx to the power 2 plus k is simply 1 over 2 mv squared. So we can cancel out this and that will go. Of course, we're going to remain with Ka equal to Kx squared plus mv squared. From here, this can go this side, so we're going to have K s squared minus Kx to the power 2 equal to mv squared over m over m. Cancel out this, you're going to find that the velocity squared will equal to k a to the power 2 minus kx to the power 2 over m. Now remember that we can do some mathematics. We can factor out this, so we can factor out k, so it's going to be k over m, then of course going to be a to the power 2 minus x to the power 2. Now remember that omega is equal to the root of k over m. Then of course if we add the power 2 this side, then remove the square root, so omega squared is equal to k over m. So meaning, but before that, you can introduce the square root everywhere, meaning our velocity is going to equal to root of k over m. Then of course this and that will go, that and that will go, so we're going to have a minus x. That's the formula for velocity, of course in meters a second. Now since we know that omega is equal to k over m, square root of k over m, while there is square root of k over m, we can replace with w. Therefore you can take note of this formula, so formula 1. But in case maybe you have been given omega instead of the spring constant and the mass, you can simply use this formula. You can replace omega there and simply put x here. This formula can also work. You can use this formula, it will give you the answer. Okay. Now from here, we know that another formula for omega that you must be able to know is this. Omega in terms of frequency is equal to 2 pi frequency. Okay, you can take note of that formula. Now if you want to make the frequency the subject, then automatically you can cancel out with 2 pi everywhere. 2 pi, this and that will cancel, and the frequency is going to be omega over 2 pi. Now remember that omega, by now we know it is simply square root of k over m over 2 pi. Okay, so let me try to wrap this. Okay. So this is very simple. It's just a matter of understanding. So of course we have frequency is equal to square root of k over m over 2 pi. So this can also be written as frequency is equal to 1 over 2 pi the root of k over m. So in case you are asked to find the frequency, you can use this formula provided you have the spring constant and m, which is the mass. So you take note of that formula. Now another formula that I want to show you. Let's try to relate everything now to the period. Now we know that period is just inversely proportional to the frequency. So we're saying that the period is equal to 1 over the frequency. Okay? And at the same time, frequency is equal to 1 over the period. Now, remember that omega, we said that omega is equal to 2 pi frequency, but we know that the frequency is equal to this, meaning where there is frequency we can put 1 over t, and we're going to have a t here, meaning if we make period the subject, we're going to have 2 pi over omega, which is just the same as t is equal to 2 pi over the root of k over m. So from here, this is just the same as period is equal to 2 pi the square root of m over k. So you take note of this particular formula. Okay, so having known all this, you are able to solve all the questions that are under simple harmonic motion, regardless of how difficult the question is. If you apply this concept, then automatically you are able to come up with the answers. So in my next tutorial, we will be learning how to solve practice questions. So don't forget to subscribe, don't forget to comment. Shalom, shalom. Thank you so much.